Okay, everyone, thanks for coming again to another ONEPAS meeting on the mathematics of thin structures. Today, we're very pleased to have Gilles Francfort from Paris XIII. And as you can see, he'll be talking about moving beyond membranes. Gilles?
Well, thank you. Thanks for the invitation. So that's the title. Last week, Irene kind of set up the context of dimensional reduction, and then she detailed what happens when you're at the lowest order. That is when once you've rescaled, you have energies that are of essentially order 1. And what I am tasked with is to go beyond that, so to see what happens when your energies scale at a higher order. So I'm going to try and do that, and I feel both very comfortable and very uncomfortable doing that for the following reason. I've never worked beyond membrane. So what I'm doing is essentially kind of trying to tell you in a nutshell my probably only partial understanding of what it involves. So I know there are I know among the people who are listening to this talk, there are people who are much more qualified than I am to talk about those regimes. So I hope they won't be mad at me or disgusted by my ignorance. And please, if I say something which is too outrageous, don't hesitate to interrupt me if I say something which is not correct. So yes, so let's go to the next one. Of course, now it doesn't want to shift. Let's see. So now, so sorry, before it, oh, good, okay. So, oh, no. No, so, okay. Let's see if, no. Do you know what's happening here? I don't. Anyways, so one of the problems that I'll go back to this, but throughout my talk, I'm going to consider the energy which is thought to be the energy which is the right one for finite elasticity. That is so I'm going to be within the context or the setting of hyperelasticity. So I have an energy density W, which acts on 3x3 matrices, which are supposed to be the gradient of the deformation, and which take its value in R, or may take the value plus infinity. And it is frame indifferent, so which means that, for those who wouldn't know, but I don't know if anybody here doesn't know, which means that when you pre-multiply your 3x3 matrix by a rotation, you get the same value of the energy. Furthermore, it's a non-negative energy, and it is 0 at the identity. So it's minimum at the identity. And we're going to assume some kind of smoothness near the identity, let's say, in a small neighborhood of the identity. And we're also going to assume some that when you're close to the identity, essentially you're quadratic. So that's what is written here, that W of F is greater than the square of the distance to the rotation. And because of frame indifference, using polar decomposition, you can show that this distance squared to the identity, to the rotation, is the same as taking the F transpose F, which is a symmetric matrix, taking its square root and evaluating the norm of its difference to the identity. The norm, what I mean by norm of a matrix is the Frobenius norm. So the trace, the norm of A is the square root of the trace of A transpose A. So if you put all this together and you compute the Hessian matrix as the identity, which I will call Q3 throughout the talk, what you get is that Q3 is definitely positive as a quadratic form acting on symmetric matrices. So if you specialize Q3 to symmetric matrices, you get something which is definitely positive. Now, I'm going to call, so this is a bit different from what Irene did. I'm going to call Q2 for a 2 by 2 matrix. So Q3 acts on 3 by 3 matrices, right? So I'm going to take 2 by 2 matrices, F prime, and I'm going to complete them to be a 3 by 3 matrix by adding zeros. And then I'm going to call Q2 what I wrote here. Okay, so I'm adding a third column to F prime, and I'm minimizing over all possible third columns. So C is a vector in R3. Okay, so now I'm going back to Irene's notation, I think. So I'm calling, so omega H is your domain, which has a height H. And as she explained last week, it's better to rescale. So to place yourself on a fixed domain, which I called omega, which is S times minus 1/2. So S is the midplane, it's the midsection of your plate, if you want, and it's flat, right? And to call gradient H or nabla H the rescale gradient, because when you perform this change of variable, which consists in stretching in the third direction, you introduce a 1/H when you differentiate with respect to that direction, the transverse direction. So this is FH, and now, so obviously, let's see what happens here. Yeah. So now I recall what Irene said last time. So if you have an energy which is, let's say, P coercive with P growth, which is not the case of the energy I just described here, then at order 0, so when FH is independently of is bounded, let's say, independently of H, the gamma limit, so for that order, FH gamma converges, let's say, strongly in LP or weakly on bounded set of W1P, it's about the same thing, to an energy which is defined in the following manner. So it's the integral over a section over S, over the horizontal section of the quasi-convexification of W bar. And W bar is what happens when you take your original energy and you minimize with respect to the third column. And that the quasi-convexification is the usual formula for quasi-convexification. And your field U, your target field, only depends on the in-plane variables, X, which I denote by X prime, which she denoted by X prime. And the nabla prime means only in-plane derivatives. So it's a two-dimensional problem, but with a field which goes into 3D. So U, the target for U is 3D, but it only depends on two variables, okay? Now, one thing that I don't believe she mentioned, and which goes back, so this is the original result, the alpha result, if you want, of Ledre and Raoult. And one thing Irene may not have mentioned, but that I'm going to mention here, is that in performing this quasi-convexification and this infimizing process of the third column, you get something which keeps frame indifference. So if your original energy is frame indifferent, your membrane energy is also frame indifferent. And that makes sense because R is in SO3, F prime is a 3x2 matrix. So what I'm writing makes sense. Okay, one thing to remark is that and that's also in Ledre-Raoult's, is that if you take short maps, that is, if you take maps whose gradient, which I call F prime here, are such that there are singular values, so the eigenvalues of F prime transpose F prime are less than 1, then when you compute the energy associated to those short maps, you get 0. And this is also in Ledre-Raoult. So what does this correspond to physically? It corresponds to a compression. So under any kind of compression, be it uniaxial compression or biaxial compression, your model gives you 0 energy. So that's not much information, right? So that means that it is probably not the right order for example, compression, which is intuitively what you think of when you think of a membrane. A membrane is something you stretch, not something you compress, right? I don't know if that's the right way to think about it, but anyways. All right. So now, as Irene had noticed and remarked in her talk, membrane theory does not accommodate the type of energy that we got in that we have in finite elasticity or in hyperelasticity. And I refer to the blue star. The blue star means all the assumptions about my energy. To my knowledge, there is one exception, which is incompressible membranes. And that's a work of Conti and Doltzman from 2008, where they show that in the case of incompressible membranes, you can accommodate the kind of energy which blows up as the determinant goes to 0. And you get the same result that you would get for that Irene showed last time, except that when you compute the inf, you have to compute it under the constraint that the determinant should remain 1. And when you do that, you get a model where the resulting energy is only finite on rank 2 matrices. And this is very simple to understand, because if you have a rank 1 matrix, so in the process of computing the membrane, you have to do an infimization process over the third column. If you have a target field whose gradient is only rank 1, there's no way that you can find a third column so that suddenly would be rank 3. So you got to get an infinite energy. So that's to my knowledge, and I may be wrong here, and if not somebody else knows something about it, they may please say something. To my knowledge, this is the only case where you can truly accommodate an energy of finite elasticity in the membrane regime. Now, I should be fair and quote the ongoing work of Hafsa Anza and Mandalena. So first there was some work in the late 90s by somebody by the name of Ben Belgasem, who I'm not sure is in mathematics anymore. And what he did is he did the membrane, he did the dimensional reduction for membrane with an energy which is a little bit more closer to finite elasticity. It's an energy which is only finite when the rank of your matrix F is full. So it doesn't have the properties that the determinant should that the energy is infinite for all matrices with determinant, non-positive determinant, but only for non-zero determinant or zero determinant. So you understand what I'm saying. So that was a result, and it gave hope that you could get also the membrane energy for the case that is of interest to finite elasticity. Unfortunately, I don't think there is a definitive result now, but there is ongoing work of Hafsa and Mandelela, where they little by little build energies that resemble more and more that of finite elasticity. So that's what I wanted to say before I go on to the topic, to higher scale. So now I'm going to go to a higher scaling. So the typical assumption is going to be that your energy on the rescale domain is not bounded by a constant, but by a constant time 8 to the beta, where beta is some positive number. And the goal is to find the gamma limit in the appropriate topology, let's say weak W12, for example. And see how robust those results are to various things, to boundary conditions, or to if you set them up as minimization problems. And I will comment on this later. And for this, the two foundational papers are those of Friesecke-James-Müller, and you have the references. And what they use in a completely decisive manner is rigidity. So just a few words about rigidity here. So rigidity says essentially, for those who don't know, I don't know if anybody, maybe you all are very familiar with it, but I have to assume somebody might not be. So rigidity says the following. Let's say you have a function, and let's say it's good, a vector value function whose gradient is a rotation. What can, at each point, what can you say? Well, a very simple result, if you have, for example, u which is h1, and its gradient is a rotation at every point, then it's a fixed rotation. And the proof is a one-line proof, so I'll say it. It is an identity that for any distribution u, with values in R3, so it's an algebraic identity if you want, that the divergence of the cofactor matrix of gradient u is 0, okay? But here gradient u is a rotation, so it's a divergence of the cofactor of a rotation. But so some people call cofactors the adjugate matrix up to a transpose, but okay. So, but for a rotation, the cofactor matrix is itself. So the divergence of this rotation should be 0, but this rotation is gradient of u. So you get that u is harmonic. And because u is harmonic, if you compute the Laplacian of the norm of the square norm of the gradient of u, you get 0. And you compute what it is because it's harmonic. No, I'm sorry. That's not it. Because you compute the Laplacian of the square norm of grad u squared. Because grad u is a rotation, grad u squared is 3 in 3 dimensions, or 2 in 2 dimensions. So its Laplacian is 0. But when you compute the Laplacian of grad u squared, you have a term which involves the Laplacian, which will be 0 because the Laplacian is 0, and another term which is the square of the Hessian matrix. And so you get that the Hessian matrix is 0, and thus grad u is a fixed rotation. So this is called exact rigidity. Now what we're interested in is, or what is going to be instrumental, is approximate rigidity. And what is approximate rigidity? It tells you that if you're close to a rotation at each point, you're close to a fixed rotation. Of course, close in which norm? And the theorem that was originally proved by Friesecke-James-Müller, and then there were many extensions, is that it is an L2 type theorem. It tells you that if you're close to a rotation in L2 norm, you're close to a fixed rotation in L2 norm, but it's not one, as you see on the slide. There's a constant, and that constant is invariant by, I should have written translation in dilation and dilation of your domain. Okay, so this is the tool which is going to be the primary tool in the analysis. And as I said before, there are many extensions of that result, but we're only going to use this result. So I had prepared a proof, but I'm not going to do it clearly. I won't have time. So I'm going to go to. So this is going to be there are two kind of heavy slides. So I'm going to go through the first. So remember, my energies, which depend on H, are bounded by by a constant times H to the beta, and H, and I'm going to assume that beta is at least 2 here. So first, so I'm on the domain S cross minus 1/2, 1/2. So what I'm going to do is I'm going to apply the approximate rigidity result to small cylindrical tubes or tubular neighborhoods which pave my domain. So what do? I take a regular grid of size H on my base, and then I extend it to be a tubular neighborhood, so kind of a parallel pipette of the form which I wrote here, SAH. So I'm going to apply rigidity here. So what I'm going to do is I'm going to descale, go back to the domain of height H, so that I am, and then I'm going to apply. Why do I do that? Because the rigidity result is for gradients, not for rescale gradients. So I do that. I apply the rigidity. I get a constant. Then I rescale, and I get the rescale gradient, and I get the statement which is after the arrow, which tells you that there's an RH, which is a rotation, a fixed rotation in SO3, such that I have that estimate. And then I use the fact that this constant is invariant by dilation and translation to say that I can find. I put all those elements together and then I get the green star estimate, which is that I can build this kind of piecewise constant rotation, which satisfies the same estimate, but this time globally over my domain. And so this is a little bit trickier, the red star. The red star tells you that the estimate that I wrote here, which tells you how the rotation varies from point to point when you vary, so this rotation depends only on X prime, right? It depends only on the in-plane variables, because that's the way we constructed it. And then it tells you how it varies when you go from one point to the next. It's not so hard, but it's a bit complicated, so I'm not going to do that now. So I get this estimate, and it is a fundamental estimate that is going to be used repeatedly in the various proofs. So that estimate, you see, it depends on the translation, z squared, and it depends on h with this kind of powers. So now I use the red star. How do I use it? I use it, I mean, I'm not using it. They used it that way. So what they did is they essentially said, well, you know, that tells you that that tells you that what I wrote on the right, that tells you that essentially you have a compactness in L2 of your RH. And so using, because of a Friesecke-James-Müller type argument, and so it tells you that RH converges strongly in L2. You knew that RH converged weakly because RH is a rotation, so it wasn't hard to say that it converged weakly, in particular in L2. But this tells you more. It tells you it converges strongly in L2. And because it converges strongly in L2, it converges to a rotation, okay, which I'll call R bar. Now, because of the green star, because of the green star inequality, if you want, it tells you also that the rescale gradient of UH converges strongly in L2 to the same thing, to a rotation R bar. But you know, that's what Irene did last time, that this rescale gradient converges to a pair grad prime u, so the in-plane derivatives du dx1, du dx2, and a third column b, which is a limit of 1 over h duh dx3. So you get that grad prime u b is actually a rotation. But not only that, because of the same red star estimate, when you divide by z, you see that as you go to, and then you let h goes to 0, when you divide by z squared, you get that the limit is bounded by a constant. And that tells you that the differential quotient of RH, when you go in the in-plane direction, is bounded uniformly by a constant. So it tells you that R bar is actually not only an L2 function, but a W12 function. So you have, so this is a remarkable thing, very unusual. Your limit has more structure, more regularity than your original fields. Okay, so here you get the structure. You get that both the rescale gradient and the rotation go to a fixed isometry, and B, because it's a rotation, has to be the wedge product of the du dx1 by du dx2. Not only that, but if beta is greater than 2, when you divide in the red star inequality, when you divide by z squared, you get still some h that's left on the right side. And so when h goes to 0, it goes to 0. So it tells you actually that the differential quotients are 0. So R bar is not a function of x prime anymore, it's fixed. So there are two different regimes here. So first, let's forget about beta less than 2. I'll come back to this later. But if beta is greater than 2, is greater than or equal to 2. So if beta is 2, you get R bar, which is a rotation, which depends on x. So you get an isometry. But if R bar is greater than 2, you get a fixed R bar. So it's a fixed rotation. Okay. So with this, I'm going to go to the case beta equals 2, which I'll explain in some detail, and then I'll tell you very quickly the case beta greater than 2. So the case beta equal 2 is the original paper by Friesecke-James-Müller, and it's a nonlinear bending case. So, we consider this expression GH. So what is GH is just well, it's you read it. So it's very because of the estimates that were on the previous page, this GH is clearly bounded in L2. Okay. So it converges to some G in L2. Now, if I write my original energy in terms of GH, W of the rescale gradient of UH is W of I plus HGH. So now I'm going to use something which just comes from my original assumptions on the elastic energy. If I take a matrix A, W of I plus HA is bounded from below by what I wrote here. Okay. So if I take the limit of, I want to do the gamma limit. So if I take the limit of the integral of W of grad H UH, I get that it's greater than 1/2 of Q3 of G, because G, AH, so GH plays a role of A here. So it's greater than 1/2 of the integral of omega of Q3 of G, which is the same thing, which is in turn greater than 1/2 of the Q2 of G double prime. So remember, Q2 was what happened when you put 0 as a third line and a third column, and that so you get this automatically. So now we would like to determine. So we guess. So here the guess is this is going to be the gamma inf. So what do? We have to compute G double prime. But in order to compute G double prime, what we're really going to compute is G prime. What is G prime? G prime is what I wrote. So it's nearly the same as G double prime, but I haven't canceled out the third line. How do we compute G prime? So by computing the integral from x3 to x3 plus z, so this time z is not anymore an in-plane variable, it's an out-of-plane variable, of duh dx3. So you write what it is. That's what I wrote. 1 over z uh minus something. And now you try to pass to the limit. So first, you know that duh dx3 converges strongly in L2, that's what was on the previous slide, to a b which depends only on x prime. So this integral divided by 1 over h z converges exactly to b. But now, so you know that this quotient 1 over z uh at x3 plus z minus uh at x3 over h converges strongly in L2 to b. So you keep this, okay? And if you go to the line below, it tells you that when you differentiate this with respect to the in-plane variables, you converge in h minus 1 strongly to the in-plane gradient of b. So that's the right side of that convergence. But what is this grade UH of x prime and so on? Well, it's what I wrote. It is exactly what you would do if you perform this difference, 1 over z RHGH translated, okay? Which now you can pass to the limit in the left-hand side of this equality, because you know that GH converges weakly, but RH converges strongly in L2. So you can pass to the limit, and what you get is the next line, which is R bar times this quotient of G prime. So it's so only the two first columns are of interest to us. And this is exactly the same as saying what I wrote as the next line, which is that dg over dx3 by letting z go to 0 is what I wrote. So what you get in the end, so this is a little bit, okay. What you get in the end is that the 2x2 matrix, which is made of the two first line and two first columns of dg dx3, is equal to what I wrote on the right. And in particular, it is independent of x3. And so you can write that the 2x2 matrix G double prime is what it was on the mid plane plus a linear dependence on x3 times dg over dx3 double prime, which you know how to compute. This is all there is. So now, once we have that, we plug it into the relation which is at the top, that is the lim-inf inequality, and we get this. We get that Q2 of G double prime is Q2 at G double prime of X prime 0. And since it's quadratic, you have a linear term and a quadratic term. But the linear term involves X3 in a linear way. So it's going to go away when you integrate it from -1/2 to 1/2. And so you're left just with the 0th order term and the quadratic term in X3 squared. And you just forget about the constant term. You keep only the quadratic term, and that gives you a candidate for the gamma limit. That's the candidate is what I drew in red, and the expression which involves this dg dx3 is exactly the one that comes from the previous slide. Is that object grad u transpose grad b, and that object is just the second fundamental form, the curvature tensor associated to S, as I wrote to the right. So now, of course, it could be so that we went too far down because we neglected the term in Q2 of G double prime. So you need a gamma lim sup argument. I'm clearly not going to do the gamma lim sup argument, but roughly, what are you going to do? You're going to do what you do for all those problems. You're going to mimic the process. So you're going to take a u hat, which is an isometry. You're going to take the associated b hat, and then you're going to construct UH the way I wrote it. D hat is the result of the minimization process with respect to the third line and third column. Okay, and you do that, and so you get that. No, you haven't gone too far down, and this is your energy. So the result of Friesecke-James-Müller is what I framed in red. So it involves a quadratic form. So it's a nonlinear bending model. It's quadratic, but it's quadratic in terms of the second form, which is not a linear expression in terms of u. So this is the result for the case beta equals 2. For the case beta greater than 2, in view of the time, I don't think that I'm going to go through the details. It's essentially the same principle. The first thing one has to notice is that R bar, as I said before, because beta is greater than 2, is independent of X prime, so it's a fixed rotation. So we might as well set it to be the identity. And then we play with exactly in the case beta equals 2. In the case beta equals 2, if you go to the middle of that slide, I'm sorry, I don't have any way to underline things. Where it says set as before, so before we had GH with what was 1 over H BH, and I'm not expecting you to remember what BH was, but BH in the case beta equals 2 was just essentially what is on the third line of this transparency without the H2 minus beta over 2 in front. So it's just RH transpose grad H UH minus the identity. Because there's a beta, which is different from 2, you have to modulate this by H2 minus beta over 2. So it creates some complications, but essentially the proof is pretty much the same, although the limit kinematics is different. So I'm going to just go to the limit kinematics now. So let's see, I don't, sorry. Participant. So, yes. No. Okay. So I go to the. So first, before I go to the limit kinematics, note that so it's the last line on this slide. So the limit, as before, it involves the same kind of quantity. So as before, you drop out the zeroth order term, except in one case, the case beta equals 4, for reasons which are not clear to me, but maybe somebody can explain it. And so what you get in the end is what I wrote here. So you get, so the limit kinematics is a bit different. It involves a field V, which is a limit. I wrote it here, but it's lost. It's in the middle of this slide. So it's a rescaled transverse displacement, which converges strongly in H1 to V, and that involves only this quantity, and it's only a function of the in-plane variable, so it involves this Hessian of that V. And so the model you get is a model like this. So the first line is what happened for beta different from 4. And for reasons which are a little bit more complicated, which I cannot explain here, it so happens that when beta is less than 4, you need to impose an additional constraint, which is that the determinant of the Hessian of V is 0. For beta equals 4, that the only case where you cannot drop in this gamma limit inequality is a zeroth order term. And this is the famous von Karman regime, which involves the zeroth order term. And for beta greater than 4, it's the same as for beta less than 4, but you don't have this constraint on the determinant. And so those are the results. So it tells you essentially everything for beta greater than or equal to 2. It gives you, in terms of the scaling of the energy, as a function of the thickness of the plate. It tells you which regime you should expect. Okay. So so two things are missing. First, what happens when beta is, so Irene was talking about the case beta equals 0. I've been talking about the case beta equals 2 or higher. What happens in the case beta strictly between 0 and 2? Well, not so much is known. There's work of Conti and Conti-Maggi, which essentially tell you, so you know you're converging, your rescale gradient and your rotations always converge to a grad prime mu b, But because you with beta less than 2, I should come back maybe because beta is less than 2. This time, you do not have strong convergence of RH to A to R. You only have weak convergence. And so you don't know that the limit is a rotation. And because you don't know that the limit is a rotation, but so the only thing you know is that RH transpose RH is the identity because RH is a rotation. And so by, if you want lower semi-continuity of the weak limit, all you can say is that the limit U is a short map. So it satisfies this inequality, grad U transpose grad U is less than 1. So what Conti and Maggi could prove is that for beta less than 5/3, the gamma limit is trivial. It's 0 for short maps and infinity else. For beta equals 5/3, they don't know what the gamma limit is. All they can say is that they can say a little bit more about those short maps. They can say that there are origami maps. So there are piecewise affine isometries. So they're not isometries, but they're piecewise affine isometries. And they make the analogy with the picture of an origami, and then they make the analogy with the crumpling of paper and confinement. So what happens when you take a piece of paper and you confine it, you crumple it. Okay. And I'll come back to this. And for beta greater than 5/3 but less than 2, nothing is known, as far as I know, even today, 20 years later. Okay. So now, what about the boundary conditions? So all that I've talked about now is free of boundary conditions. So essentially, there was no boundary condition. What happens if you impose a boundary condition? Well, if you impose, for example, the most natural boundary condition, you say you clamp your plate. So no zero displacement on your boundary. Well, it changes completely the picture. For any beta strictly greater than 0, not in the membrane case, but for any beta greater than 0. So it's again the work of Conti, Maggi, Müller, and they get a completely different model, which I'm not going to describe here, which is called the Foppel-von Karman model. And it's completely different. First, it goes right across scales, so it doesn't depend whether beta is 1, 2, or 3, or up to 4, and I'm not sure about the strictly less than 4, but it's a completely different model, which I'm not going to explain right now. Okay, so that's one result. And what about the nonlinear bending, for example, the case beta equals 2? Well, the only kind of boundary condition that we can impose that keep that nonlinear bending is essentially the boundary condition that is used in constructing the attainment sequence. So the only kind of boundary conditions is something which is of the form U of x prime plus H x3 B of x prime, where UB is an isometry. If you depart from this, then you don't recover nonlinear bending. So boundary conditions are you're very limited. So yeah, no, before I go there, so let me say that again. Boundary conditions, only certain boundary conditions seem to be workable, and they give rise to, except if you tailor them to the attainment sequence in your gamma convergence process, they give rise if they're known, to completely different models. Okay, so now you could, so now I come to maybe my conclusion. I think it'll be a good time, which is my personal conclusion on this. And then, so here is my conclusion. When you perform, when you perform homogenization, which is a different ball game, what you get models, you get homogenized models with which, on the whole, are completely local. They do not depend on the fact that on the kind of boundary conditions or the kind of right-hand side in your equations, if you want, or linear terms that you add to your energies, if you want, that you care to add. This is not true here, except in one setting, the membrane setting. In the membrane setting, and I don't know, I don't think Irene really made this, focused on that point, but the membrane regime delivers the gamma limit in the membrane regime is local in the sense that it applies to any open set. Here, it's completely different. And this independently of the boundary conditions that you can apply. Here, it's completely different. Be it in the nonlinear bending or in the other regimes, you need to specify either you have no boundary conditions or you need to specify your boundary conditions in a very particular way. So I would argue that the models that are obtained for beta greater than 0 are not models of plates. They're solutions of specific boundary value problems. And so I would say that so this is my personal take, and I take full responsibility for what I'm saying. But I would argue that from the standpoint of mathematicians going to mechanicians or to people in engineering and telling them, aha, you got the wrong model when you use this von Karman with this kind of things, because we've proved that through gamma conversions and dimensional reduction that we obtain a different model, is a bit too much, because really we don't have models. We don't have performing models. We just have limit solutions of a bunch of boundary value problems which depend on a small parameter. Let me further that point with the way that it's presented in especially the second article of Friesecke-James-Müller, where they prefer to so in the way I presented this in terms of scaling of the energy. They presented it in terms of scaling of the forces that are applied. So what are they doing? They're adding to their energy a term of the form FH-UH. And they argue about the order of FH. But that's fine, you can do that. But when you're doing that, you're doing something which has absolutely no applications. Because in finite elasticity, there's only one force, the gravity. If you depart from gravity in any way, shape, or form, so if you apply pressure, or if you apply any kind of other forces, you will not get a linear contribution to your energy. So you won't get a linear term minus integral over omega of FH-UH. For example, if you apply pressure, then in your energy minimization, you should get something which depends on the cofactor of the gradient of the scale cofactor or the cofactor of the scale gradient. I don't know. So something which completely destroys your energies. So in a way, this consideration in terms of the order of forces is completely in my opinion, is not the right thing to do. Finally, what about short maps? Well, short maps, I suppose, so there's a mathematics literature around short maps and crumpling and so on. So I just took a picture of a piece of paper, a sheet of paper. Actually, I got it from the Conti Magic article, although I could have taken that picture myself. So do you think that's crumpling? Well, I don't think that it is crumpling. And the reason is, this is not elasticity. Because if it was elasticity, once I put my sheet of paper on on the table, it should there are no forces applied except with the table. It should go back to where it was. It's not. And even if you come back and you stretch your sheet of paper, you will see ridges and things like that. So there's clearly more to crumpling than finite elasticity. There are energies that are dissipated. There's energy which is being dissipated in the folds, and I don't know what it is. But so crumpling and confinement goes beyond, in my opinion, the fact that you can solve this limit process for beta equals 5/3 or beta between 5/3 and 2. So this is kind of my critical view, personal, of the regimes from the standpoint of mechanical models. Of course, it is a completely different matter if you view that in geometric terms, and if you're interested in the geometry and so on. So, for example, I look forward to the talk by Marta Lewiska, but those are different. Those are different. The worries are of a different order. I think I should stop, and I thank you for your attention.
Very nice talk. Shall we open up to questions or comments? Anybody? Just fire away. You have the right to unmute yourselves.
Gilles, I have a question. So maybe it's more about membrane model. The short map, the short maps not being visible. I'm thinking about this problem of a stretched thin sheet with wrinkling, and there seems to be two things going on. On the one hand, the energy scaling, since it's basically pooling, you have membrane model, but the wrinkling, these are low energy phenomena, and so you have the globally very high energy scale, and yet you don't see, when you ignore low energy terms, you don't see the patterns.
Yes. So what is your question?
So the question is, other models that why do you not see the patterns? You are like retaining the higher order terms. Why these patterns appear? Why don't we see the patterns? What are the models that would be able to describe them?
I don't know. And couldn't you say that the same thing happened when you go to beta greater than 4, when you get some linear model of bending, so you get some linear bending, but you forget, you don't recover the classical Kirchhoff love type kinematics of linear elasticity, right? So isn't it a little bit the same thing? That so for those who are not used to it, if you start with a linear elastic material and you do this kind of dimensional reduction, you get a model which mixes together bending and membrane type. And this you cannot recover from nonlinear elasticity that I know of. Maybe I'm wrong. So it's the same thing. And that's a classical model which is being used by engineers with Kirchhoff law. Yeah. So I think that's a bit the same criticism. You know. You're going in my you're reinforcing my thoughts on that.
Yes, in fact, I had them and I tried to voice them, but I couldn't express them as clearly as you did. So I was very happy to hear them.
I have a quick one, if I may. These are problems that come equipped with lots and lots of experimental work, I would imagine. So my curiosity here is, have experimentalists been able to find configurations that achieve any of the or like arbitrarily many values of the beta? Like, can you hit anything in this range, or are there only certain values that have been observed experimentally?
Well, so I don't know what does it mean, an experiment? I mean, the question is, let's say even the forces where let's say I don't know. Let's say the I have a thin structure and I'm walking on it, right? Okay, and let's say it was there was no problem with dead forces, or but let's say so what is the scaling of your forces with respect to H? You don't know. So there's no way to there's no way to compare those models to any kind of experiment, right? All you can say is, I recover something which looks like what people are using when they're building a bridge, but that's about all that you can say. Maybe the situation would be a bit different if you were able to get what in homogenization is usually called corrector type results, where somehow you can say UH is U is a good approximation of UH, and the order of convergence is such, but there are no results like that I know of. So from this standpoint, you cannot compare to experiment. All you can compare is the model that you obtain. Does it resemble a model which is used in the engineering literature or not? And mostly it is, which I think is an incredible, because look at von Karman, which I didn't detail. It's an incredibly complicated model. The fact that mechanicians have come up with that model, I think is remarkable, actually. Yeah.
Thanks.
Gilles?
Oui, Benoit. Yes, Benoit. Yes, Benoit.
Yeah, I was just curious, is there something like this when you go from 2 to 1 dimension? Would there be a way like that you could get some intuition or idea?
Yes, there is. I know nothing about it. You can go from 2 to 1 or 3 to 1. So and you have a whole pathology. The expert, there's an expert who's still online, Maria Giovanna Mora. I don't know if she wants to say a word. Is there a huge difference between 3D 1D and 3D 2D? Maria Giovanna, maybe she's online, but she's not online.
Yeah, no, I'm online. Hi everyone. No, but well, what I can say is that there is you can deduce a full hierarchy also when you go from a 3D to 1D. And what happens is that, well, many things are simpler in the sense that you end up with functionals defined on functions of one variable, which is somehow the mid-fiber of the beam. But typically, since you are going to zero in the cross section of the beam, typically you have to take into account this in the limiting energy density. So in a sense, you have a richer structure that you are sending to the limit, and you see that in the expression of the limit in energy density. And yeah, and well, this is what I can say in a few words, I think.
Thank you, Maria Giovanna.
You're welcome.
Thank you.
And just, but then,
yeah, go ahead, Benoit.
for example, in this case, you have the same picture that boundary conditions just make a whole mess of your study, or like,
yeah, there are the same kind
okay.
of things concerning the boundary conditions and the applied forces too. So if they are compatible with the kind of structure that you get for the limiting deformation, then it's okay. But if you try to do something different, then yeah, you find the same kind of difficulties. Yeah.
Okay, thanks.
You're welcome.
And if that's fine, I had another question, but I'm guessing the answer is who knows. Could you also understand what would be the dynamics of those objects? Or is it just completely science fiction if you don't even understand the static part?
I think that's a very good question. And so first, it depends on what you call dynamics, okay? So if the dynamics is adding kinetic energy, then, well, there is a little bit, there is some work. Once again, I should defer to Maria Giovanna, who knows much better the literature. There is some work. Did you do that work, Maria Giovanna, with Stefan Müller?
Yeah.
Okay. So she can explain them. Well, I'm sorry, I told you from the get-go that I never worked in that field. Okay, go ahead.
Well, in the dynamic case, I think the main issue is actually to have existence of solutions for elastodynamics in 3D. And because then, I mean, otherwise you don't have deformations to pass to the limit. And so what we were able to prove is that for higher scalings of the energy, so the one corresponding to beta equal to 4 or higher, then you can show existence of solutions for elastodynamics. So usually under quite strong assumptions, you can only guarantee short time existence. And what we were able to prove is that if you are in the regime, so if your forces are such that you are in the regime for beta equal to 4 or higher, then you can have an estimate on the existent time independent of h, and you can also pass to the limit. And so get the corresponding, well, basically you get the dynamic model in linearized elasticity or in von Karman. And I think this is what has been done in elastodynamics. I mean, not, I don't know of any other result on this line, I mean, following.
And just to be clear, the equation in the limit are all linear.
No.
Or,
No. For beta equal to 4 is the von Karman case, so you still have some non-linearity.
Huh.
I don't know if Gilles, I don't remember if Gilles showed the.
No, I didn't write the complete thing because it involved an additional variable which I hadn't defined. So I left the von Karman case kind of muddy.
So it's not completely linear. So there is still some non-linearity. It's almost linear in the sense that it's in terms of the displacements. So you're still looking at small deformations.
May I add something, if I may?
Sure.
Even without kinetic energy, imagine that you're applying a force to something. First, you're not applying a force. You're applying, you have to get there. So even if you're in equilibrium, you have to get to that force. So really you're ramping up your loading process. It's different for boundary conditions, for forces. You're ramping it up. when you ramp it up, your forces get bigger and bigger till you reach the force that you want to apply. So which regimes, how does this interact with the asymptotic process? That's not clear to me. So you know, should you say for very small, maybe it's stupid what I'm saying, but should you say for very small times, you of order H4, and then you, as the time grows, you of order H, I don't know. So this is really also an issue, I think, you know. So which the regimes should depend on the amplitude of the force. I don't know. So I guess this is also on my part a criticism of static problems with forces, at least.
Thanks.
Any other comments or questions? Okay, well, let's thank Gilles again. Thanks a lot.
Thank you, everybody.
Thanks.
Thank you, Gilles.
You're welcome. Thank you for staying till the end.
And as a reminder, next week we'll be back with Marta Lowica.